In this video, we're going to look at the first of three types of giant structure. The first being metallic structures. So metals make up the vast majority of the periodic table. Around 75% of the periodic table are metals. And metals exist in an endlessly repeating lattice arrangement, so like a regular pattern of metal ions surrounded by delocalized electrons. And it's this attraction between the positive metal ion and the delocalized electron that allows the metallic structure to hold its shape, so to hold its structure. First thing we're going to do is look at a definition. The first definition being metallic bonding. And so metallic bonding is the attraction. And we must say it's like a force of attraction. Don't just say it's a force, it's an attraction. And we must say that it's to delocalize electrons. Do not just say electrons, it must be delocalized electrons. And in any question where we're relating a property of a metal to this bond, we must actually state what the bond is, rather than just saying because of metallic bonding. You need to say because of the attraction between the positive ions and the delocalized electrons. This is a strong force. Okay, so this is a strong force of attraction. We must refer to it as such. So in metals, positive metal ions are packed close together in a regular way, and that is called a lattice. So this is called a giant metallic lattice. Giant metallic lattice, the metal ions are surrounded by freely moving electrons that are able to move, and we call those delocalized. So when we talk about delocalized, what we mean is that they are spread out over more than one atom So they're not tied to the atom that they came from. So they're spread out over more than one atom. In a covalent structure, if we have delocalized electrons, we would say that they were spread out over more than one bond as well. And when we talk about giant, we mean that the lattice is endlessly repeating. It doesn't have a defined end that we can think of. The number of delocalized electrons that you would have in the lattice would depend on the number of electrons that are lost from the metal atom when it becomes the ion. So think about the group number or the oxidation state on the metal. So if we're being asked to draw a label diagram of the metallic bonding in sodium, so sodium is in group 1 of the periodic table, which means it has one outer shell electron. So when we're drawing a label diagram, what we need to be doing is remembering 1 to label it. We've got to show a regular lattice structure. So we need to show a regular pattern. We're looking for that you are going to show us at least 2, ideally a few rows of a regular repeating pattern. So make it have a pattern. I'm going for 9 circles to represent, and I've put them in nice lines to represent that they're regular. Now these are representing the Na, but remember ions, so Na plus positive ions, group 1, 1 plus. So I'm going to put a 1 plus charge in each one. Okay, each one of these released an electron. Now the electrons are freely moving, so don't make them appear to be in a regular pattern as well. So just try to dot them around, but not too regularly. Make sure that they have a minus charge attached to them. So squeeze them in, make sure that they are not appearing to be in the same pattern, and label those delocalized electrons. How would the diagram differ if it was magnesium? Well, magnesium is in group 2. So it has 2 outer shell electrons that it loses. But the principle of the diagram is the same. You want to draw a regular pattern. So you want to have your lattice arrangement, and you need to have at least 2 rows, ideally something that shows that pattern. These are going to be Mg2 plus ions. So this time I'm going to put a 2 plus in. Okay, and that's our Mg2 plus ion. And then because magnesium releases 2 electrons, I'm going to add in more, remembering that these are not supposed to be regularly arranged. So try to get your electrons in. Try to look like you've got more electrons than ions, because there's 2 for every Mg2 plus ion. So this is showing a giant metallic lattice. So what properties does having a giant metallic lattice give us? So when we're talking about them, the question will often be phrased, describe the structure and bonding in, and then name of a metal. So describe the structure and bonding in magnesium and explain how this leads to, and then it'll ask you about one of these properties. So the structure and bonding, the structure is that it is a giant metallic lattice. And the bonding is metallic, but when you're describing the properties, you will probably need to say it's the attraction between, and you'll possibly need to say that this is strong to describe a property. So it's attraction between positive metal ions and delocalized electrons. We can see that there's a metallic lattice being drawn for us. So these are our positive ions. And then they have just drawn a minus charge for the delocalized electron. That's fine. Just be careful not to put it into a circle, because if you put the minus into a circle, you're starting to make your diagram look ionic. Okay, so the melting point. What can we say about the melting point of metals? Well, we know that metals exist as solids at room temperature. We have to heat them quite a lot to melt them. They must have high melting points. So why do they have high melting points? Well, it's because it takes a lot of energy to overcome, and the word we want to include here then is, if we're going to use a lot of energy, we need to say that the forces are strong. So it takes a lot of energy to overcome the strong attractions. In fact, let's put the strong forces of attraction. And what are those attractions between? Strong forces of attraction between positive metal ions and delocalized electrons. And this word delocalized is very important. So don't forget that we've got to have that in there. And it's a force of attraction, not just a force, because a force could be of repulsion. Metals conduct electricity when liquid or solid because the delocalized electrons, again, this word delocalized, very important. So because the delocalized electrons can move, and they're what carries the current. Malleable. Malleable means that you can, if you use a hammer on a metal, you can bend it into a new shape. It doesn't shatter the metal, it just bends it. So we're not going to break it. So why can we do these things? We can also pull metal into thin wires without it snapping. So why can we do that to metallic structures? If you try to do that to an ionic structure, the crystal would just shatter. If you hit a crystal with a hammer, it would just shatter into lots of pieces. If you hit a metal with a hammer, it will bend into a new shape. So why is that? So metals are malleable and ductile, and that is because the layers of the ions, if you were to bang this metallic structure with a hammer, the layers of ions in the giant lattice can slide over one another and it doesn't break the metallic bond into new positions without disrupting, because the attractions between these freely moving electrons and the positive ions, sliding the layers of ions over another doesn't make them repel each other. It just means that the forces are still there because the delocalized electrons are moving and holding it. So we don't disrupt the force of attraction between the positive ions and the delocalized electrons.